I said at the beginning of Chapter 5 that the finite element method is primarily useful for solving problems in more general 2- and 3-dimensional domains. So far, all we've been doing is using it in 1-dimensional problems where the advantage over finite differences is not so pronounced. So let's look at a 2-dimensional problem, and one example in 2 dimensions would be to divide the 2-dimensional region into triangles and use piecewise linear elements in triangles. This is directly analogous to using the Chapeau functions of section 5.2, except it's a 2-dimensional problem. We'll define our S sub I to be the piecewise linear function. That is, it's going to be a plus bx plus cy in each triangle, where a, b, and c will be different in each triangle, but such that S sub I is 1 at its node and 0 at all the others. So for example, S sub 3 would be 1 here, 0 here, 0 here, 0 here, 0 at all the others. Therefore it's non-zero only in these 3 triangles. Those are the only 3 triangles that include 3 as a vertex. Any other triangle, S sub 3 will be 0 at all 3 vertices, therefore 0 exactly 0 in the entire triangle. So it's 0 in all of this area, only non-zero here. It looks like a little pyramid. It's going to be 1 here and 0 at the others. In this figure, we've assumed that this solid boundary here is the essential boundary, and the rest of the boundary is the del R2, the natural boundary. And notice that I've given negative node numbers to all the nodes on the essential boundary and positive numbers to all the vertices not on the essential boundary. In other words, in the interior or on the del R2. Then we'll expand U as always as omega plus linear combination of phi, where the phi are the SI for I positive. In other words, the phi are the basis functions, the piecewise linear functions, which are 1 at vertices that are not on the essential boundary, i.e. either in the interior or on the natural boundary. And the omega will be the summation of R times SI for I negative. In other words, sum over the vertices on the essential boundary. That ensures that at any point on the essential boundary, omega is equal to R. R is assumed to be the given Dirichlet boundary condition on the essential boundary. So at any point on the Dirichlet boundary, the essential boundary, omega will be equal to R, and or at least it will be equal to R at the nodes there, and it'll be an interpolant to R at other points, I should say. So it'll be close to R, and phi will be 0 on the entire, each of the phi will be 0 on the entire essential boundary. Therefore, U being omega plus a linear combination of the phi will be equal to R on the essential boundary, at least at the vertices on the essential boundary, and it'll be in a linear interpolant to the essential boundary condition on the rest of the essential boundary. Now, before we give an example, let's talk about error bounds, and as always we ask the question, how close can we approximate the true solution of our partial differential equation by an interpolant, and we assume that the Galerkin method will be approximately as good as the interpolant, and that's a straightforward interpolation, polynomial interpolation problem. Since it's a first degree polynomial, we expect to have order h square error, and we do, where h is a measure of the triangle diameter, largest triangle diameter, say. Now the matrix will be sparse again. It's very much like what happened with the Chapeau functions. a sub ik will be 0 for most I and k unless I and k share a common triangle. So for example, A13 would be 0 because S1 or Phi1 would be non-zero only in those two triangles. S3 is non-zero only in these three triangles. There's no overlap. Therefore, in every triangle in the entire region, either Phi1 or Phi3 or both are 0. So the AKI will turn out to be 0 and A13 will be 0. And if we have a dense triangulation with lots of triangles and lots of vertices, most of the elements of the matrix will be 0, so it'll be sparse. However, if we're using a band matrix to solve the linear system, then we don't just want it to be sparse, we want to have a small bandwidth, and that's a little trickier in 2 dimensions. It depends on how you order the vertices. If you have a regular triangulation like this, then typically you would just order the vertices, and therefore by ordering the vertices you're ordering the unknowns and the equations. 1, 2, 3 up through n plus 1, n plus 2, etc. And that will keep the bandwidth down to n, I guess. But in a more general region with a unstructured triangulation, the best ordering to minimize bandwidth is not nearly so easy or obvious. One popular method is called the Cuthill-McKee ordering. Basically, you start at a corner and call that vertex 1, then you number all vertices that share a common triangle with 1, 2, 3, etc. Then you go to vertex 2 and look for all unnumbered vertices which share a triangle with that. Remember, sharing a triangle with vertex 2 means if vertex I shares a triangle with vertex 2, that means A2I will be non-zero. So we're trying to keep I and k close together if aik is non-zero. So we're trying to keep vertex numbers close together if they share a common triangle. So we go to 2, number all as yet unnumbered vertices of 2, starting with 4. That's the only one. Then we go to 3, number all of its neighbors that haven't already been numbered, and there's only 1, 5, and so forth. So that's a Cuthill-McKee that isn't guaranteed to minimize the bandwidth, but it does a reasonable and fairly simple to calculate, does a reasonable job of minimizing the bandwidth. Okay, in the next section, 5.6, we're going to write a little Fortran program to solve a fairly general linear 2-dimensional problem with linear triangular elements. We're going to develop a program which solves this problem again, only the 2-dimensional analog, except that we're going to assume that P and Q are 0, so on the natural boundary condition it'll just be the normal derivative equal to 0. And here is the code, and as usual it's simpler than one might think. Here we define the initial triangulation and give the vertices and node numbers of each vertex in the triangulation. We're using a relatively small number of triangles. In this particular example, we've got a triangulation of a region into 16 triangles. Now we need to calculate the elements of the matrix A and the elements of the right-hand vector B, and we do that in a element by element assembly. That means instead of picking an I and K and calculating all the entire integral corresponding to AIK, we go triangle by triangle, and each triangle we calculate the contributions of that triangle to all of the elements of the matrix A and the right-hand side B. And so for each triangle we calculate each of the 3 phis. There'll be phi and phi x, phi y corresponding to each of the vertices. We calculate omega at each of the 3 vertices. And here we actually calculate the contribution of this triangle, triangle K, to any of the right-hand side elements BK and any of the matrix elements Ki. And notice the formulas. BK, the contribution of the triangle, actually triangle KTRI, to all the K's which are non-zero in that triangle. Here's the formula. Now let's go back and look at the formula for BK and compare. Okay, remember from section 5.1, here's your BK. It's the integral over the entire region of F phi k minus D, gradient of omega dotted with gradient of phi k minus A omega phi k, and we're assuming that Q and P are 0, so we don't have that term. But here's what has to be integrated in BK. Now compare that to our calculation of BK. And we're actually using an integration scheme. All integrals are calculated just using a midpoint scheme. That means the integral of anything we want to integrate is approximated by the value of that function at the center of gravity, the midpoint of the triangle, times the area of the triangle. So we're integrating F times phi k minus D times omega. Well, this is the dot product of the gradient of omega with the dot product of phi minus A times omega times phi k. That's exactly what we need to integrate. So we're evaluating that at the midpoint and multiplying it by area. Similarly, for the A matrix, we have D times the dot product of phi k and the gradient of phi k and the gradient of phi I plus A times phi k phi I. All that's evaluated at the midpoint times area. That's the thing that we have to integrate to calculate AKI. Then we solve the linear system, and little a are the coefficients of the phi k. And that's it. Pretty simple program. It's only 16 triangles, and we compared the exact solution with the true solution at one point, and the error was relatively small, out in the third digit, surprisingly small considering we only had 16 linear triangles. Now, of course, just like in the one-dimensional case, you can use higher degree polynomials. Linear elements are by far the easiest to program, but just like in one-dimensional case, we could use cubics, and in fact, PD2D, my finite element package, uses up to 4th degree polynomials and naturally gets higher order accuracy. In fact, with 4th degree, piecewise 4th degree polynomials, you get order h to the 5th accuracy. Okay, now let's talk about time-dependent problems. Can the finite element method be used for time-dependent problems also? Yes, it can. For example, here's a linear time-dependent problem with Dirichlet boundary condition and Neumann boundary condition and initial values. For the Galerkin method, as usual, you multiply by phi k and integrate and do an integration by parts. And you approximate u by omega plus linear combination of the phi i's, but now the phi i's are the same phi i's as before. Whatever we have used for the phi i's for the steady state problem, we can use those again. Those are not time dependent. The coefficients a sub I are going to be time dependent, and so we multiply our time dependent differential equation by phi, integrate over r, integrate by parts, end up with what? You end up with an ordinary differential equation system for the unknown a's, which are now functions of time, i.e. you end up with an ODE system like this, where a is the vector of unknown coefficients, but it's dependent on time. The coefficients of the phi I are now time dependent, and so we end up solving an ODE system for this vector of coefficients a. And as you might expect, this is a very stiff system, just as it was for finite difference equations. And therefore, this ODE system should be solved using implicit methods, preferably the backwards difference methods. And in fact, in the next section, there's a one-dimensional example, partial differential equation, where we use the Galerkin method and end up with the ODE system, which is stiff, of course. And as evidence that is stiff, look what happens when we use Euler's method to solve the ODE system. The typical symptoms of stiffness: when delta t is very small, everything's fine. When delta t is not very small, above a certain threshold, it goes unstable. On the other hand, if we use backwards difference methods, and here we used fourth order backward difference formula for solving the ODE system, and the errors are just fine, even with much larger. Here's delta t equal to 0.1, and we get the results are just fine in spite of the large delta t. And as you might expect, you could also use the collocation method. Same expansion for u is omega plus summation of linear combinations of phi I, where the coefficients are time dependent. So either Galerkin or collocation, you expand u in that form. And the difference, of course, is with the Galerkin method, you multiply by phi k and integrate by parts. So the collocation method, you simply evaluate both sides of the partial differential equation at your collocation points. Either case, Galerkin or collocation, you end up with a ODE system that looks like this, and in either case it's stiff and you need to use backwards difference methods, backward Euler at least. We can also use the finite element method to solve eigenvalue problems. As you might guess, the Galerkin method, you multiply the partial differential equation by phi k, integrate by parts, get a weak formulation. You again expand u as a linear combination of the phi I. There's no omega this time because the boundary conditions for an eigenvalue problem have to be homogeneous, so omega is always going to be 0 for the eigenvalue problem. So u is simply a linear combination of the phi I. Now the ai are not functions of time. This is a steady state problem. However, you end up with naturally an eigenvalue, matrix eigenvalue problem of the form a little a equals lambda b a, where little a is the vector of coefficients a sub I. It's the eigenvector, lambda is the eigenvalue. If you use collocation method, of course, you simply evaluate both sides of the eigenvalue partial differential equation at your collocation points, and again end up with a system like this. This is called a generalized matrix eigenvalue problem, and as we discussed in chapter 4, there are various methods for solving it. The only one we looked at is the inverse power method, or shifted inverse power method. Naturally, you could just multiply by B inverse and you'd have a regular matrix eigenvalue problem. That's not a good idea for two reasons. One, B will generally be sparse, whereas B inverse will be full, and you'll end up with a full system. And another reason is that in the symmetric case, A and B, for the Galerkin method anyway, not for collocation, A and B will be symmetric, whereas B inverse A will not be symmetric. That makes it harder to solve. And finally, we want to look at an eigenvalue example. It's a two-dimensional problem in a rectangle of this form: divergence of d times gradient of u equals lambda u, where the d is actually a discontinuous function. It's defined to be 1 in the left half of this rectangle and 2 in the right half. Notice that we have on three sides essential boundary conditions. On the top we have Neumann type boundary condition. But the interesting thing about this problem is that d is discontinuous. It's equal to 1 on one side and 2 on the other. Now, we simply cannot use the collocation method on this. Why? Because the collocation method, we would have to use the product rule on this, and we would get d times the Laplacian of u plus gradient of d dotted with gradient of u. And the problem is you've got first derivatives of d in there, and d is discontinuous, so the first derivatives are infinite at the interface. You simply can't use collocation method on this. However, you can use the Galerkin method, because the Galerkin method, remember, starts from the weak formulation in which there are no derivatives of d, only d itself. Here in section 5.1, this is the A matrix for a steady state problem, but it's the same for the eigenvalue problem. You have d times the dot product of the gradient of phi k with phi I, and there are no second derivatives of phi k, which means you can use piecewise linear triangular elements which don't have continuous first derivatives. That's okay, because there are no second derivatives involved here. But in our case, d is discontinuous. That's not a problem. There are no derivatives of d here. For the Galerkin method, for the collocation, there are. So in the case where d is discontinuous, it's a problem for the collocation method, but not for Galerkin. So we could have used the piecewise linear elements as in section 5.6. We actually use PD2D, which uses a triangulation of the region but uses fourth degree polynomials. But the fact that d is discontinuous is not a problem for the PD2D Galerkin method. In fact, the first eigenvalue is accurate to 5 significant digits. And here's the eigenfunction corresponding to the first eigenvalue. Using PD2D, you can sort of see the discontinuous derivatives in u there.